All right, we'll do one-dimensional collisions. Okay? And watching you guys leave school in the parking lot, that's mainly two-dimensional collisions, and we'll talk about that next time. But for right now, just one-dimensional collisions. And that means particles are interacting with each other along a straight line. Okay. So let's review a little bit. We said this, that, well, we defined momentum. And we use a letter P for momentum. And we said that the momentum of an object is just quite simply the mass of the object times its velocity. Notice it's a vector, okay? And the direction of the momentum is just the direction of your velocity. You're just multiplying the velocity by the mass of the object. Then we had the impulse momentum theorem that we just developed. That is, that the change in momentum of an object will be equal to the net force acting on the object integrated over time. Force times time. And notice that, again, your change in momentum is a vector. Your force is a vector. So it's the change in momentum, the direction of the change in momentum will be in the same direction as your net force, which, of course, makes a lot of sense. And we also, well, we kind of developed everything we need to know to do one-dimensional collisions when, from section 9.1, when we really defined linear momentum and its conservation. But let's kind of let's rederive it all, because it's good for you to see, and I don't think many of you have done the homework for it anyway. So let's talk about a collision here. And so here's like some flat frictionless plane. And I'll have object 1, and I'll put it on wheels. So object 1. And I'll put a spring on it. Nice little spring with a little plunger on it. And this is, so we're not going to create any, through all these collisions, at least for right now, we don't have to worry about friction or any of that kind of stuff yet. And here's object 2. And let's say object 1 has its own mass, and it has its own initial velocity, and it's headed towards object 2. And they're going to smack into each other. Okay, they're going to collide. Well, what happens during a collision? Let's look at these guys while they're colliding. Now, this is before the collision. And when you're doing collision problems, it's very handy to draw a picture of the situation you've got before the collision happens and then after the collision. You know, what are the objects doing before the collision? What are they doing after the collision? What I'm going to draw here is a before, during, and after picture. So let's just say object 2 is at rest, and object 1 is moving towards it. So this is the before picture. Now, during the collision, here's object 2, and here's object 1. And the spring is getting all scrunched in. Okay, so here's 1 and 2. But these objects, object 1 and object 2, they're interacting with each other. Right? They're applying forces to each other. Now, what did Newton have to say about the forces that object 1 applies to 2 and 2 applies to 1? What did he have to say about that? Yeah, They're equal and opposite. So here's a force. This is the force of object 1 on object 2. And equal and opposite to that is the force of object 2 on object 1. And Newton said, Newton's third law describes the fact that when objects interact with each other, they always apply equal and opposite forces. No exceptions to this rule. It is a fact of our universe that this happens.
You said Newton.
I said Newton. This is true no matter what.
Okay.
I mean, look, some of the physics that we learned that Newton gave us has been modified. Like, you get close to the speed of light. Some of the kinematics that we use don't apply anymore because you can't exceed the speed of light. Gravity. Newton gave us a law of gravity. And some of those equations don't quite describe how nature behaves. So we have general relativity for that, which hopefully some of you will learn when you're grad students. But this law, this third law, it's always true. Whether you're dealing, here's what's cool about it. The third law is true whether you're talking about subatomic particles, the smallest particles we can observe, or you're talking about clusters of galaxies colliding, the largest structures in the universe colliding. This is true. Okay, I mean, this analysis, the equal and opposite forces, it's true. It's very, very interesting stuff. Anyway, now here's what I think you can see. And your notebook is on your desk. Thank you. Now, I'm going to, this will look kind of silly, but let's let my hands represent these two objects that are colliding. So when they collide, here comes object 1, and then they collide. Bam! Okay, let's do that again. Bam! Now, what are my fingers representing here?
The opposite forces.
The equal and opposite forces, right. Bam! Now, what does the bam represent? It represents, okay, I'll do it this way. Watch this. No, you're making stuff up now, Gage. All right, no, here we go. It goes like this. It goes, time! Does that make it better? Yes, it does. All right. Time! Okay, that's representing the amount of time that these forces are applied. And what do we know about the amount of time that this force is applied and the amount of time that this force is applied? They are the same amount of time. Another, you could also say, duh! Okay, yeah, they're applied. The forces are hitting each other. They're applied for the same amount of time. So let's multiply the force times the amount of time that the force is applied. Well, what is this? Force times time. Force times time, we just said, is force times time is impulse. So really what this is this force times the amount of time that that force is applied represents the impulse acted on object 1. And that impulse is also equal to the change in momentum of object 1. So the change in momentum of object 1 will be equal to the change in momentum of object 2, but in the opposite direction. Okay, the impulse momentum theorem and Newton's third law combined together tells us that the change in momentum of object 1, because of the collision, will be equal to the change in momentum of object 2, but in the opposite direction. Really a big idea. This is true if you've got little choo-choo train cars, you know, or you've got maybe the object 1 and object 2 are galaxies. This could be the Milky Way, and this could be the Andromeda Galaxy, and we're going to collide in a couple billion years. It's going to shred our galaxy. I'm not worried about it. That's my great-grandchildren to the 18th power have to worry about that, but, you know. Well, actually, it wouldn't be 18th power. It would be like 7th. It's still so much I don't care. I don't care. Sorry, future generations. That's your problem. But our galaxies will collide. Oh, here's the cool thing about when galaxies collide. The space between the stars is so vast that probably no stars will actually physically collide. But they will gravitationally collide. The interaction, this interaction force between the two galaxies will be the force of gravity. And that force will fling stars and squish gas clouds together, and we'll have a vast era of star formation, and it'll be quite exciting to watch. But you'll have to be very, very patient. Yeah, because the collision will happen over hundreds of millions of years, and you know, so you'll probably change the channel if you have to wait that long. All right, but anyway, now let's rearrange this and see what we get. It's something that we got before. Right. Okay, the change in momentum.
Each second's probably like 1,000.
Yeah, you'll have to. Now just add the change in momentum of object 2 to both sides. Now, don't get lost in math. We're using math, okay, because look, we have a plus sign and we have deltas and letters and stuff. So yeah, it's math. But we're using it to represent something that's a concept that's very true. This is how much momentum object 1, this is how much we changed the momentum of object 1, and let's add to it how much we changed the momentum of object 2. And when I add up those changes in momentum, I get 0. Which means that overall, if I make these two objects my system, there's no change in momentum of my total system. Yeah, this object gets its momentum changed, and this object gets its momentum changed, but the whole system added together, there's no change in momentum. And so let's break this down even further. This, and by the way, we get really lost in subscripts here. Sorry, there's going to be a lot of subscripts here. This is M1 V1 final minus M1 V1 initial, right? This is the change in momentum of object 1. Does everybody agree with that? Plus, we need the change in momentum of object 2. Well, that's just going to be M2 V2 final minus M1 M2 V2 final. Right? So, initial, dang it. See, we're getting lost in a subscript swamp. So the final minus the initial for object 1, the final minus the initial for object 2. And this will all equal 0. Well, I didn't really need these parentheses, did I? So here's what we often do. Let's just put all the final stuff on one side and all the initial stuff on the other. So I'm going to leave the final stuff. I'm going to say M1 V1 final plus M2 V2 final. This eraser is really bad. V2 final equals Now add M1, V1 initial to the other side. And then add this one to the other side. And this is an equation I can use to solve a problem. I mean, what are you going to be given when you have a collision problem? You're going to be given, probably given the masses, and you're going to be given like the initial velocity and the final velocity of one of them or something. But something's going to be missing, and you have to solve for it. So now I want you to go back, and I think it's posted online now, but when we did the first video on momentum, we basically got the same idea. This, if I add, oh, by the way, these are all vectors. I should put vector hats on these guys, right? Now, right now, we're dealing in just one dimension. It's all going to be either in the x direction or the y direction. Later on, well, there's nothing in any of this analysis that assumed that it was one-dimensional. So this works no matter what. But these velocities are vectors. So P final equals P initial. Now, what was the main assumption that allows this conservation of momentum to be true? That the final momentum will be equal to the initial momentum. The assumption was that the only force acting on these objects was internal to my system. Okay, because look, here's my system, object 1 and object 2. And there's no net outside force from the outside world that's changing the momentum of either of these guys. So that's the big idea. If there's no net outside force acting upon your system, the momentum of your system will not change over time. The momentum of the individual particles within your system can change. Look, object 1 gets its momentum changed. Object 2 gets its momentum changed because of the collision. Now, I failed to draw my after picture. I'll just continue it on here. So before, during, you got these forces, and then let's go up here to look at after. Now, does object 1 keep going forward? If object 1 had more mass than object 2, it will continue moving forward. If object 1 had less mass than object 2, it'll actually bounce off. We're going to do a little activity, believe it or not. We're going to do a lab activity where we demonstrate that. So after the collision, let's say object 1 is a little bit lighter than object 2. So object 2 moves off in this direction. Maybe object 1 goes kind of slowly, bounces off the other way. But here we've got this object had its momentum changed. This object has its momentum changed. But when you add those two changes together, you get nothing. You get 0. Okay. Now, what if you have okay, there's two different kinds of collisions we're going to talk about. And now we're going to bring in energy. Let's suppose in this example that I started with, this is a spring. And that spring gets compressed, and then it flings them apart again. And there was no heating of the environment. There was no sound. We didn't lose any mechanical energy. Well, in that case, we call that an elastic collision. And in an elastic collision, there are two things that are true. the initial momentum will equal the final momentum. Now that's always true for no matter what kind of collision you've got. In a collision where you're saying, hey, there's no net outside force acting on your system, you have an isolated system, but two particles within that system are colliding, this is true. Law of nature. Now, if we don't heat anything up, if we don't lose any mechanical energy, well, then we can say this is true. Well, actually, let me start here. In elastic collision, the initial mechanical energy is equal to the final mechanical energy. But in this kind of system right here, where we look, before there's no energy stored in that spring, right? And then after they spring apart, the spring is relaxed again, and there's no energy stored in that spring, so we don't have any potential energy stored in the spring. So what we can do with that is say, hey, look, let's just say that the initial kinetic energy of our system will equal the final kinetic energy of the system. Okay? So you can say these two things are true if you have an elastic collision. I hate elastic collision problems. I hate them because they're hard. Let me show you why they're so difficult. If I have a two-particle collision that's elastic, I have these two equations. I have, well, the initial equals the final momentum, so m1 v1 final plus m2 v2 final equals m1 v1 initial plus m2 v2 initial. Okay, final moment. Oh, I switched the order here. It doesn't really matter. Now that's true. And then you also have this for kinetic energy. Well, if the kinetic energy is equal before the collision and after, as it is after, so there's my final kinetic energy, and that will be equal to my initial kinetic energy before the collision. Okay, so here are my two equations. Now, if you have two equations, you can have two unknowns, right? Okay, now I defy, this is really hard. To solve these two equations simultaneously is, well, it's a really bad word. I'm not going to say it, okay, because it's being recorded.
You could take out 1/2 and
Okay. Now, we have solved these equations for, let's say you want to solve it for V1 final. Maybe that's what you want to find. So you solve this for V1 final, or maybe you solve this for V2 final, and then you plug it in here, but it gets squared. Oh no. And it becomes this monster algebra problem. And I remember the first couple years I taught this class. I mean, I'd seen it done. I'd actually done it before, and I tried to do it, and I got hopelessly lost and wasted 20 minutes of class time trying to do the algebra of solving these two equations simultaneously. So I don't do that anymore. I mean, I have had students for a couple points extra credit. They'll bring it. If you solve it and bring it in, I'll show it to the class and pat you on the back, give you a couple points. But it's been done for us. I'm just going to say, here they are. Let's zoom in here and we'll talk about these. This is in your book. No.
You just rederive it every single time. But is it like the relationship between those two equations? You can rearrange it and you'll basically get that.
Yeah. So, like, what if what if you want to know V1 final? In terms of the masses and the initial velocities. I mean, let's say what your two unknowns are. Well, you know the masses, you know the initial velocities. What do you want to find out? Well, after the collision, what are the final velocities going to be? And it's an elastic collision. Holy smoke, if all they give you are the masses, the initial velocities, and you start with these guys, okay, good luck. It's all right, but someone's already done all the hard work for us. If you solve those two equations simultaneously, here's V1 final in terms of the initial velocities and the masses. What? 262. And here's the equation set up for V2 final. Now, it is doable. If you're really good at algebra, at keeping track of everything and not losing a sign and not messing up, this isn't really all that bad. It takes a couple of pages. For me, it's terrible. It's like algebra hell. Algebra hell. No, never mind. But anyway, you can use these. So, read, obviously I want you to read the book because it's talking about the same stuff I'm talking about.
Wait, so say like we're doing a kind of problem like that with the AP test. Would an AP grader go like, oh, okay, I recognize that?
Hey, look, that's a great question. What about the AP test? I have never seen an AP problem where you have to do this.
Oh, okay.
Now, on the AP test, you don't go in with your own equation list. You go in with the equation list they give you. And these equations are not on there. But I've never seen a problem where you have to derive them or use them. But there are a couple homework problems where you have elastic collisions, so I'm showing you them so that you can. So sometimes in physics we just say, hey, the math people figured it out for us. There it is. If you're the kind of person that has to do it yourself, well, good luck, do it, bring it to me, I'll give you a shoulder hug, congratulate you, it's awesome. All right, oops, let's zoom out again. Now, elastic collisions are not all that common at the macroscopic level. If I have cars with really good springs on them, it's a good approximation. But in reality, almost all collisions of big size objects that we can see. Now, by the way, gravitational collisions are usually quite often modeled very nicely as elastic collisions. Or if I have a proton colliding with another proton, that's an elastic collision. But when you rear-end your car into the person in front of you, that's an inelastic collision. Those are much better. The reason why they're better is because, well, momentum is still conserved, but now we're going to lose some of our mechanical energy, and it gets turned into the internal energy of the environment, the molecules in the environment, or the atoms, and we're going to warm stuff up. Now, here's what I mean. Next time you're driving in a car, if you slam into a tree and the hood of your car gets all bent and scrunched up, okay, hopefully you were wearing your seatbelts and have airbags, because now you'll be conscious and probably not that badly injured. Get out of your car and then feel the hood. It'll be a little warm. Okay? Because some of your kinetic energy was absorbed by the molecules, and now they're vibrating a little faster. And it created, it heated the environment. Yes?
Or because your opponent's gas tank exploded.
Your what?
Or because the other car's gas tank exploded.
Well, that would be a great deal.
You have to assume ours didn't because we're still alive.
Okay,
So.
you don't get to change my example problems. All right. So in other words, the initial kinetic energy of your problem will be greater than the final kinetic energy. Right? You're going to lose energy. Non-conservative forces will be at work. Will be doing work. And taking your mechanical energy away. As sound and heat, it's just going to go out into the environment. Here's a classic example of that. Do any of you ever go shooting? Yeah, you go shooting? Have you ever shot a bullet like into a sandbag or into a block, and then you go feel the bullet right after it's hit? It's really hot. And that's because you have changed the kinetic energy of the bullet into the internal energy heating the bullet. Thanks. Can't do it right now, though. Yeah, no, can't do it right now.
So let's go back. Come back to it. I didn't have more slides.
Yeah, that's good. Or you can leave it here, but
I didn't have it all signed.
yeah, I'm doing this right now. Okay, so, but in any case, this is your basic equation. When you have a 1D collision, or even a 2-dimensional, which we'll do next time, but a 1D collision, time, all right? No, just bam. All right, think this way. Okay, this is the first equation you write down. Okay, my initial momentum will equal my final momentum. And then you break it down to this. And then you just fill in the pieces and solve for your unknown. They're actually pretty easy problems once you've got this figured out. Okay. Why don't you do some example problems from this? There's lots of them. And then we'll get to work. Okay, anyway, that's it. Bye.